Welcome to section 4.4. We are continuing our discussion on logarithmic functions, exponential functions, and in section 4.4 we're learning how to solve logarithmic equations. Section 4.4 is kind of a combination of all the rules that we've already talked about. There's not really any new concepts here. We're just learning how to kind of put it all together, and we're going to be practicing slightly more difficult equations. So hopefully, if you're coming into this section with a relatively decent, solid grasp of the material we've taught earlier, that we've earlier discussed in chapter 4, you should be okay going into section 4.4. So we just got a list of examples to look at. No, there's not any new rules. In example 1, we want to solve log of x minus 3 equals 4. Notice we do not see a subscript for our base, so we know that means that we're working with the common logarithm, which is base 10. So if you put the 10 there, and think about how you might approach this, this is a good problem where you can convert to exponential form using Logi-Froggy. So I'm going to say 10 to the 4th equals the inside of my log function. And I've never learned how to draw good frogs, but there's my frog. So that gives me 10 to the 4th equals the inside of my log function, x minus 3. And then we just solve this for x. 10 to the 4th gives me 1,000. No, I'm sorry, it gives me 10,000. 10 to the 4th is 10,000 equals x minus 3. And then if I add 3 to both sides, I get 10,003 equal x. And that's a good answer because if I put 10,003 back into the function for the x, I'm still taking the logarithm of a positive number. So that's a good answer. It does not violate my domain. Just remember, as you're going through these, if you happen to get an x value that if you were to go back and check, substitute it back in for the x inside your function, if it has you taken the logarithm of a negative number, that would be an extraneous solution that you would have to toss out. So just remember that we have to be careful that we're not taking logarithms of negative numbers. Let's look at example 2. Example 2, part A. Solve log base 2 of x plus log base 2 of x plus 2 equal log base 2 of 6 plus 1. So we've got an equation. You've got two logarithms on the left and you've got a logarithm on the right. Think about the properties that we discussed in section 4.3. We had a product property for logarithms. We had, or maybe we called it a rule, a product rule for logarithms. We had a quotient rule for logarithms, and we had a power rule for logarithms. Do any of these apply here? If we just ignore the right side and just look at what we have on the left, log base 2 of x plus log base 2 of x plus 2. This is a good candidate for our product property for logarithms, or product rule, because these are being added together. So they have the same base. You can write it as log base 2 of, and then you'll do x times the inside over here, x plus 2. So we have log base 2 of x times this x plus 2 equals, and then over here I'm just bringing it down on the other side. Okay, so we used a product rule to get us to this point. And now we have log base 2 of this equals log base 2 of this. All right, so here's another rule that I can use. Do you know what it is? I've got logarithm of this equals logarithm of this. They have the same base. This is the one-to-one property for logarithmic functions that tells us if we take the logarithm, if you have two logarithms that are equal to one another and if they have the same base, that allows you to drop the logarithms and just set your the inside of the functions equal to each other. So we can just drop the log part and we'll have x times x plus 2 equals 6x plus 1. And now we just have a basic quadratic equation. Let's distribute. That's x squared plus 2x equals 6x plus 1. With a quadratic equation, we need to set it to 0 and see if we can get it to factor. So I'm going to subtract 6x and I'm going to subtract 1 on both sides. And that's going to give me x squared minus 4x minus 1 equals 0. can I get that to factor? Alright, that's not going to factor, so if it doesn't factor, we'll go to the quadratic formula. And I'm a little bit cramped for space now. I'm going to come, I don't like to do this, but I'm going to come over to the left side and work over here to get my quadratic formula. So let me change my color. So we're going to do x equals negative b, so that will be a positive 4, plus or minus the square root of b squared, so negative 4 squared. Put negative 4 in parentheses before you square it. Minus 4 times a is 1, c is negative 1. All over 2 times, and again a is 1. So I've got it all into my quadratic formula over here. That gives me 4 plus or minus the square root. That negative 4 quantity squared gives me 16. So 16 plus, and then 4 times 1 times 1, the double negative makes it positive, so that's just 4, all over 2. X equals 4 plus or minus, that would be the square root of 20 over 2. And this can be simplified. And I apologize, I did not give you enough space for this problem. X equals 4 plus or minus. We can simplify that square root of 20. 20 is 4 is 4 times 5. And the square root of 4 is 2. So I've got 2 times the square root of 5 all over 2. And then I can simplify that again because I have the common factor of 2 out front. So that's going to give me 2 plus or minus 1 times the square root of 5. Now, we want to make sure that these answers are okay, that these are actually going to work for us. Let's get a decimal approximation just so that we can get an idea of how much we're working with. Now I got to see if I can find a calculator that has batteries. I may have to pause for you a second. Alright, I got to pause. I'll find my calculator. So typing my 2 plus or minus square root of 5 into the calculator gave me 2 decimal approximations. I have positive 4.236 and negative 0.236. Only one of these is going to work. If I take that negative 0.236 and if I were to substitute this back into the original function, I would be taking the logarithm of a negative number. So the negative value is no good. Only the positive, the positive value, which came from the exact value was 2 plus square root 5. So 2 plus the square root of 5 is going to be my final answer for part A. Okay, so that one really was not that hard of a problem. We just had to go to the quadratic formula and be careful about how we simplified it. And we had to make sure we checked our answers. For part B, we're going to find the log of x minus log of x minus 1 equals 2. We're going to set this one up very similarly to what we've done already. Let's just concentrate on the left side first. You'll see that you're subtracting logarithms, and they're both common logarithms. They both have base 10. So this allows me to use my quotient rule. So I can say that this is the log of, and I'm going to divide x over x minus 1 equals, bring down my 2 on the other side. Okay, so I've got a single logarithm equal to a constant. Now I can convert to exponential form using loggy-froggy. Again, remember my base is 10. So I'm going to do 10 to the second equals the inside of my log function. 10 to the second is 100. That's equal to the inside x over x minus 1. And now we can solve this for x. So how would I do that? Let's multiply both sides by the x minus 1. That's going to give me 100 times x minus 1. And then if I multiply the right side by x minus 1, it'll cancel out and just leave me with my x. Now I'll distribute. So I've got 100x minus 100 equals x. I'm solving this for x, so let's bring the 100x to the right side. I'll have to bring it back up here now. So if I subtract 100x on both sides, it's going to leave me with my negative 100 on the left, and then x minus 100x on the right. And then to get what can I do on the right? X minus 100x, that's going to be negative 99x. So negative 100 equals negative 99x. And then divide both sides by the negative 99. I've got negative 100 over negative 99 equals x, so positive 100 over 99. Alright, the double negative gave me my positive, and because it's positive, if I substitute it back in, that answer should be good. For example 3, we want to solve the equation 1.02 raised to the 4t minus 1 power equal to 5. This is currently in exponential form. This is a good time to maybe take the... Let's apply a logarithm to both sides of this equation. That will allow us to use our properties for logarithms, meaning that this exponent that happens to have the t, once we apply that logarithm, we can use our power rule to move it to the front and turn it to into a coefficient. Once it's a coefficient, we'll be able to it'll be much easier to solve for t at that point. So I'm going to apply the logarithm to both sides of this. If you want to write that down, in case you don't know if you'll understand it later, I'm going to apply a logarithm to both sides. Just like you could take the square root of both sides. You can apply a logarithmic function to both sides. So I'm going to say the log of 1.02 to the 4t minus 1 power equals the log of 5. And then that 4t minus 1 for my exponent can come to the front as a coefficient. This is now I'm using the power rule of logarithms here. So I've got 4t minus 1. Make sure you put 4t minus 1 in parentheses because it's got more than one term. Times the log of 1.02 equals the log of 5. And now to solve for t, remember log of 1.02 is a constant. It's some irrational number. It can be distributed through this binomial, so that would give us 4t times the log of 1.02 minus, and then 1 times log 1.02. Equals log 5. So all I've done, I've applied a logarithm to both sides of the original equation, and then the logarithm allowed me to use my power rule to bring my exponent to the front as a coefficient. Once I did that, I distributed this irrational number, log 1.02, through my binomial. So that gave me 4t times the log of 1.02 minus 1 times the log of 1.02 equals, then the right side is log 5. Now, remember, I'm trying to get t by itself, so let's find any terms that don't have t. Maybe they need to be moved. This log of 1.02, it does not have a t, so I'm going to add this to both sides just to get it out of the way. That'll give me 4t times the log of 1.02 equals log 5 plus the log of 1.02. And I'm almost done. I can get t by itself if I just divide both sides by the 4 and the log of 1.02. So I'm going to divide both sides by 4 times log 1.02. That will give me t equals all this on the top over this 4 and this log 1.02. Now, this would be the exact form, and they also want us to give the decimal approximation, I believe, here. It actually didn't say in this one, so we can leave it like this, or we can get the decimal approximation. Getting your decimal approximation is going to be a little bit tricky to type into your calculator. So we got to be really careful. Let me put my calculator up here so you can see how I'm typing it in. Now, I'm going to do... In the numerator, notice you've got two separate terms in the numerator. So before I start typing, I'm going to open parentheses at the very beginning. So open parentheses, and I'm going to type log 5. Let me zoom in a little bit. Okay, so we're going to type open parentheses log 5. And notice every time you press log, it'll open parentheses again. So make sure you close it after you put your 5. Plus log 1.02. Close it once for the logarithm, but close it a second time because you finished typing in your entire numerator. So you should close your parentheses twice. And now press divided by. Before you begin to type into the denominator, go ahead and open parentheses a second time because you're putting in several things. So you're going to do 4 times log 1.02. Now close your parentheses once for the logarithm and again because you finished the denominator. Okay, so that gives me all this, and then I'll press equals. My decimal approximation is 20.5685. So if I carry it out to 4 decimal places, I get 20.5685. And that's the approximation. Example 4, where you need to find the exact and approximate solutions to each equation. Part A, I have 6 to the x equals 7 to the x minus 1 power. So they both have these variables in our exponents. It would be nice if we could get the same basis because we could use our one-to-one property for exponents. But for example, if you could get, let's say if you had over here, instead of a 6, what if we had a 49? 49 could be written as 7 to the second. If we could get the same bases, then that would allow us to just cross out the bases and set the exponents equal. So if you can do that, it's very helpful. But with a 6 and a 7 for a base, that's not possible. So let's take a logarithm of both sides. We can do log of 6 to the x equals log of 7 to the x minus 1. Now we can use our power rule. So bring your exponents to the front. You have x times log of 6 equals x minus 1 times the log of 7. And we have to solve these for x. On the right side, we can distribute the log 7 through the binomial. So we'll have x times log 6 equals x times log 7 minus 1 times log 7. And then to get the x by itself, we need to get all the terms that have x together. So the x log 7, let's subtract that on both sides. That's going to give me x log 6 minus x log 7 equals this negative log 7. And I apologize. I am so sorry. I did not leave you enough space to do these problems. So I'm going to keep going down this way. You might need an extra sheet of paper to do part B. What can we do on the left side? We've got x times log 6 minus x times log 7. Remember, you're solving for x. You've got to get it to where it's just x equals something at the end. So how am I going to get that from these two terms? Well, notice they've got a common factor. They both have a common factor of x, so x sitting in the front makes it a coefficient. That allows us to factor it out. So you can say that you've got x parentheses, and then that leaves you with log 6 minus log 7. Use the square bracket. Equals negative log 7 on the other side. So all I did was that x that was sitting in the front of both of these terms was my common factor, and I just factored it out and brought it to the front. But now I'm ready to solve for x. All I have to do now is divide both sides by this big piece here, this log 6 minus log 7. That will give me x equals negative log 7 over log 6 minus log 7. Now, when we go to type this into the calculator, again, we got to be really careful. As a matter of fact, it might be a good idea to, let's put in all those symbols that we need on paper for typing it in. In the numerator, I'm going to put parentheses around my 7, and then I'm going to put a square bracket around the entire numerator. And then I need to also put square brackets around my entire denominator, because that's going to tell the calculator how to do the order of operations. If you don't put these extra grouping symbols in, the calculator will not divide it the way you need it to. It will only divide it by the first term, but then it won't divide the second term. So make sure you put all those symbols in there. Alright, now we're ready to type it in. So again, let's zoom this in again. Numerator, I need parentheses, negative log 7. Alright, close the parentheses 2 times. Divide, open parentheses, log 6, close parentheses, minus log 7, close parentheses, and close parentheses again. That gives me 12.6234. I don't remember if they asked how many decimal places to carry it to. I'm going to carry it to 4. 12.6234 is my answer. That's my approximation. So they said to give both the exact and the approximate solutions. So the first value we got here was the exact solution. And then the second one is the decimal approximation. This is the approximate. And that was 12.6234. For example 4, part B, we're asked to solve 3 to the 2x minus 1 power equal 5 to the x power. So again, there's no way we're going to be able to get the same bases with a 3 and a 5, so we're going to just apply a logarithm to both sides of our function. So we can say that we have log of 3 to the 2x minus 1 equals log of 5 to the x power. Applying this common logarithm allows us to use our power rule and move these exponents to the front. So we'll have parentheses 2x minus 1 times log 3 equals x times log 5. To begin solving for x, we can distribute the log 3 through the binomial. So we'll have 2x times log 3 minus 1 times log 3 equals x times log 5. And now if we get all of our terms together, all of the terms that have x need to be together. So I'm going to subtract my 2x log 3 from both sides. That'll give me negative log 3 from here equals my x log 5 minus 2x times log 3. And now I can factor, like we did before, we can factor x out on the right side. So negative log 3 equals x times log 5 minus 2 times log 3. And now to solve for x, we can divide both sides by all of this. So we'll have negative log 3 over log 5 minus 2 times log 3. That's all equal to x. So we refer to this as our exact value. And the calculator will give us our approximation. Make sure that you're really careful how you type it in. Let's put the square bracket in the top for the entire numerator, and we'll put parentheses around the 5 and the 3 in the denominator because they're on the inside of the log function, and then put the entire denominator in square brackets as well. And then type it into the calculator just like you've got it written. So when we go to type it in, we're going to open parentheses, negative log 3, close parentheses twice, divide that by open parentheses, log 5, close parentheses, minus 2 times log 3, close parentheses twice. That gives me 1.869. So my approximation or my approximate value is 1.86. They usually ask you to carry it to 4 decimal places, so that would give us 1.8691. That's it. So, okay, so the amount A of a radioactive substance remaining after T years is given by this formula, which should look familiar to you. It looks a lot like the compounding interest formula. A equals A sub 0 e to the RT power, where A sub 0, sometimes called A naught, is the initial amount present, and R is the annual rate of decay. Now, it might not be clear in your notes. That little 0 is the subscript for A. It's not an exponent for R. So we've got A sub 0 is the initial amount, and R is the annual rate of decay. The half-life is the amount of time it takes for 1/2 of the original substance to decay. In example 5, we're asked, how long does it take for 2.4 grams of carbon-14 to be reduced to 1.3 grams of carbon-14 by radioactive decay? And we're given the hint that we can use this natural log of 1/2, or natural log 0.5 over 5,730 for R in our formula. So we're going to use the formula that we have at the top, the A equals A sub 0 e to the RT power. We're asked to determine how long, so that means we're solving for T. And we've got everything else that we need to go into the formula. So we're going to solve for T. And we can put, let's see, how long does it take for the 2.4 grams, so that's the beginning amount, to be reduced to 1.3 grams. So A sub 0, or A naught, is going to be 2.4. A, the future value, or future amount, is the 1.3. It's going to decay, so it's going to shrink. Then we can multiply by E. They gave us a value for R. If you don't want to put all this into your exponent, it's okay to use the decimal, but let's make sure that we carry it out all the way as far as we can. So on the calculator, if I type that in, I've got the natural log. So make sure you use your LN button this time, not log, but LN. There's LN right there, just beside 4. Natural log of 0.5, close parentheses, and then divide that by 5,730. Okay, now what does that mean? I'm getting this negative 1.2096 blah 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 e to the negative 4. That means that they have moved the decimal 4 places over for us. The negative 4 means I need to move the decimal 4 spaces to the left. So for R, I'm going to use negative 0. If I move my decimal 4 spaces to the left, it becomes 0, 0, 0, and then 1, 2, 0, 9, 6, 8, and I think that's probably far enough. We could go on with 0, 9, 4. Yeah, let's go ahead and put the whole thing in there. So R is going to be negative 0.0001209689094. That way we don't have to put all of that stuff into the formula, but just make sure you're carrying it all the way out as far as you can to make sure, with this value being in your exponent, if you don't carry it way out, it's going to throw your answer off a lot. So we put all this in for our R in the formula. And T after that. Now remember, it's T that we're solving for. Now what can we do to start solving this? Because the base is E, we can solve this similarly to the way we did the previous problems, where we took logarithms of both sides. But with the base being E, this time we're going to use natural log so that we can cancel it out with the base. Before we do that, though, this 2.4 is kind of sitting in the way. Let's divide both sides with that 2.4. So we've got 1.3 over 2.4 equals E to all that. 4 and then t. And what would that 1.3 over 2.4 look like if I divided that? Okay, I'm just going to leave it like it is. Now, if we take the natural log of both sides, that way we can cancel out the e and get all of this out of that exponent. So we'll do natural log of 1.3 over 2.4. And my ln e cancels. Alright, so we've got ln of 1.3 over 2.4 is now equal to that entire exponent. It looks like I ran out of space again. Okay, so we've got ln of 1.3 over 2.4 equals negative, we got negative 0.000120968094 times t. Now if we divide both sides with that long coefficient, that will give us our t. So we'll do natural log of 1.3 over 2.4 over that long decimal. That's equal to t. And let's see what the calculator gives us for a decimal approximation there. Typing all of this into the calculator, I'm going to type ln 1.3 over 2.4, close parentheses, and then divide by negative 0.000120968094. Enter. I get 5,068. They didn't say how far to carry the decimal. They just asked how long. So we can say that it's going to take 5,068 years. And that is our answer. And that is the last problem for section 4.4. So we'll be practicing these together in class. And that's it. Thank you.